All right, let's do an example here. Let's spend this lecture going over some examples following our introduction and exploration of the property relationships that allow us to calculate change in entropy of a system. So today we're going to look at two examples. One example involving calculation of the entropy change of the system, assuming constant specific heats, ideal gas behavior. And then we're going to do another problem involving ideal gas behavior for variable specific heat. So in the constant specific heat case, we're going to have equations for delta S that involve a bunch of natural logs and pressure and volume and temperature. And in the problem involving variable specific heat, we're going to be dealing with that S naught that's tabulated in IGB tables, okay, to calculate the integral of Cp over T dt, to incorporate variation in specific heat with temperature. So each problem has its own little quirk, but they all involve closed systems, ideal gas behavior. So we're going to investigate how to calculate and deal with entropy in those cases. Okay, what do we have here? We have a tank. This tank initially is composed of argon. Argon's an inert gas at a certain pressure and temperature, P1, T1, and volume, V1. Now, this tank here is filled with argon on the left and a vacuum on the right, and in the center there is a valve. So initially this valve is shut at state 1, and the argon is on the left-hand side of the tank. Now the initial pressure is 3 bar, temperature is 70 degrees C, and there's 5 kilograms of the argon, okay? Now this tank, I'll tell you right now, is insulated. So let's assume this tank is insulated. Therefore, the process, whatever it is going to be adiabatic. So I'm going to say in an insulated tank, okay? So this is an insulated tank. Now, at some point, the valve is open and the argon rushes through to fill the vacuum. In other words, we have unconstrained expansion. That's a hint. Is this going to be reversible or irreversible process? I want to think about that. So at some point, the valve is open. The argon expands to fill both sides of the tank until the pressure is the same between the left and the right-hand side. So we have a case of unconstrained expansion. What are we supposed to find? We're supposed to find the change in temperature of the argon from state 1 to state 2, and the entropy generation due to the expansion process. By the way, this is going to be a constant specific heat problem. So CV for argon is given as 0.28 kilojoule per kilogram degree Kelvin. So I give you the specific heat for argon in the problem statement. Besides, a little known fact here, for noble gases, that is gases that are on the far right-hand side of the periodic table, specific heats are constant, so you don't have to worry about variable specific heat problem. Argon here is a case. Argon is a noble gas, as I recall. So on the right-hand side of the periodic table, so specific heat doesn't vary with temperature. So you can, all problems involving monotonic noble gases are constant specific heat problems. Just a little fact. Just a little fact. Okay, so let's calculate delta S for the argon. Let's calculate delta S for the argon. Analysis. Analysis. Okay, our system, I better define our system here. Our system is the argon. So here's our system. Well, yeah, it does not include the vacuum. The system will just surround the argon. that means the system will move. The system will expand as the argon expands and you open the valve. So in state 1, the system only surrounds the left-hand side, interior of the tank. And then at state 2, the argon is at both sides of the tank, so the system is the interior of both sides of the tank, okay? Okay, so let's calculate delta S for the argon. Delta S, and that's for the argon from 1 to 2. I guess I'll drop the AR. How about just delta S from 1 to 2? Well, I'm going to assume here, no, actually we're told, well, I'm going to tell you this is ideal gas behavior. So I guess I better write it over here. Argon, AR, I'm going to write here, IGB, ideal gas behavior. So we've got ideal gas behavior. So I can immediately write constant specific heat. So I can immediately write both expressions involving delta S for constant specific heat. We have CV, Ln. Oops. This is uppercase S, so it's going to be mass of the argon times CV Ln T2 over T1 plus R Ln V2 over V1. Okay, I can do that. Or I can do CP Ln T2 over T1 minus R Ln P2 over P1. Okay, I can do both. I can do both. Now, we're told here that the volume, so what's the relationship between the final and the initial volume? I have here that V2 is equal to twice V1. So the valve is located at the halfway point on the container. So I know something about V2 relative to V1. So this ratio, specific volume at state 2 over specific volume at state 1, I know this. This is actually equal to capital V2 over capital V1. And I know these, okay? That ratio is 2. Remember, specific volume is volume divided by mass. So all you got to do is multiply each specific volume, each specific volume in this fraction by mass. The equation's balanced, and you get specific volume times mass, and that gives you volume. So I know this term. I know this term. I don't know this term here, CV Ln T2 over T1. So I need to find temperature T2. How might we do that? Let us apply the energy balance. The balance. Okay. So we have Q 1 to 2 minus W 1 to 2 is equal to delta E 1 to 2. And I'm going to neglect changes in kinetic and potential energy because the container isn't changing position. And I assume that state 1 and state 2, the velocity of the argon in here is negligible. So there's no change in internal energy. You can write that in our assumptions here. Let me put our assumptions down. So assumptions. So delta KE equals delta PE equals 0. Okay? Let's write that down. So we can first attack the heat transfer term. It's adiabatic, insulated tank. What about the work term? Well, there's no wires or electricity in there, obviously. Okay? So all that's left is boundary work. Now let me tell you what's physically going to happen. Boundary work is equal to the pressure, the integral of the pressure times the change in volume, and the work occurs at the boundary of the system. What is the pressure right here at the boundary of the system as it expands into a vacuum? What is the pressure as it flows into the vacuum to fill the space? Well, if you were to put a pressure gauge and you were to follow the boundary of the argon as it moved into the vacuum, you would find that the pressure was 0. So if pressure is 0, that means the integral of PdV is 0. Doesn't matter what the volume changes, pressure is 0. So there's no boundary work. W bound, and that's equal to 0. Why? Because pressure at the boundary equals 0. Pressure at the boundary is equal to 0. Another way of proving this to yourself is make the entire container, including the vacuum, the system. In that case, if you make the control volume the entire interior of the tank, argon and vacuum together, volume doesn't change, so boundary work is 0 again. So either way you look at it, either way you draw your control volume, boundary work is going to be 0 when you have the argon expanding into a vacuum. If it was not expanding into a vacuum, if it was some finite pressure inside the right-hand side of the tank, then it would be a matter of some other value, okay? So we got no heat, no work, therefore, delta U equals 0. Now, delta U is equal to the mass of the argon, assuming constant specific heats, CV delta T from 1 to 2. And again, delta U is equal to 0. Okay? If delta U is equal to 0, that means delta T is equal to 0. And that's equal to T2 minus T1, and that's got to be equal to 0. In other words, T2 is equal to T1. This is an isothermal process. Isothermal expansion. When a gas expands into a vacuum, the process is isothermal. And this has been demonstrated experimentally. Okay, but it seems like a strange conclusion. Isothermal expansion, because no change in internal and kinetic energy. I'm sorry, no change in potential, kinetic, and internal energy, okay? So if the temperatures are the same, that means ln of 1 is 0. So whichever equation we use, the temperature term goes to 0 because it's isothermal. So I think I'm going to work with the first equation then. So delta S 1 to 2 is equal to mass of the argon. CV ln T2 over T1 is 0 because it's isothermal. And all I have left is R ln V2 over V1, which, by the way, is V2 over V1. Okay, and that's equal to 2. Remember, it doubles volume, all right? Let's see here. The mass of the argon is 5 kilograms. Oh, gas constant for the argon. Let's see, do I have that? That would be the universal gas constant divided by the molecular weight. Let's see here. Whoops, I made a mistake here. I wrote down, hold on a minute. I wondered why this was so low. The CV for argon, that's my mistake. This is R. This is R for argon. Why is that so low? Usually CV is closer to 1. So R for argon not CV. We don't even need CV, okay? So R for argon is 0.208 kilojoule per kilogram degree in Kelvin, okay? 0.208 kilojoule per kilogram degree in Kelvin. And then I have natural log of 2. The units are kilojoule per degree Kelvin. That's a good unit for entropy. And let's see what we get here. I get 0.72 kilojoule per degree Kelvin. 0.72 kilojoule per degree Kelvin. So delta S of the argon from state 1 to state 2 is 0.7 kilojoules per degree Kelvin. Okay, so that's the change in entropy of the argon. Now, is this process reversible or irreversible? Your intuition should be, this is unrestrained expansion. It better be irreversible. And so what should Sgen be? Sgen should be positive. Entropy is generated for irreversible processes. Let's find out what Sgen is. Let's apply the S balance. Let's apply the S balance to our system. Let's see, we have delta S. It's a closed system, is equal to the integral of del Q over the interaction temperature plus Sgen from 1 to 2. Okay? Now this is an adiabatic process, so the heat transfer term, entropy transfer due to heat is 0. And so I get delta S1 to 2 is equal to Sgen. In other words, Sgen 1 to 2 is equal to delta S 1 to 2. I need to write this somewhere else. I'll write it right over here. I guess I'll put it over here. In other words, Sgen 1 to 2 is delta S 1 to 2, which is 0.72 kilojoule per degree Kelvin. So Sgen 1 to 2 is 0.72 kilojoules per degree Kelvin. Okay, so that's the Sgen, positive. Therefore, the process is irreversible. Note, greater than 0, irreversible process, i.e. unconstrained or unrestrained expansion. Remember back in chapter 5 for the second law, the 3 irreversible processes are heat transfer across a finite temperature difference, processes involving friction, and unconstrained or unrestrained expansion. Yes, this is an irreversible. This is an irreversible process. The gas will never spontaneously rush to the other side of the tank. If you did, you would find out that Sgen was negative, and that would violate the second law of thermodynamics. Sgen has to be 0 or positive. 0 if this is a reversible process, it's not. Or positive if it's an irreversible process, which it is. All right? Okay,